Hi, this is Math 2115, remote delivery for May 5th, 2020. This is part one of two parts. This part deals with numerical operations inside computers and the circuits that perform them. Use this to open with some encouragement. We're getting very close. In fact, today's two lecture components will be the end of the content. So don't quit. Don't stop believing. If at all possible, hang in there. We can do this. Grades are being earned and will be rendered. Remember, however, that the final exam is a mandatory requirement to pass the course. Last time we spoke of digital circuits and implementing Boolean logic with them. And we also talked about representing numbers in binary, hexadecimal, and decimal notation and changing from one representation to the other. Today, in this segment, we address using such common circuitry to perform addition and then subtraction. So let's begin by talking about how would you add, and let's just talk about adding binary digits. So you have a 0 and a 1, and you have different values that P and Q can take on. So this is a table. If you add 1 and 1, you get one group of 2 to the first power and 0. 0 units of 2 to the 0 power. Both of these you just get 2 to the 0 power, 1 unit of that. If you add 0 to itself, you get 0. So you see, this is the outcome that you get, and that is what we get from the input-output table of a circuit called a half adder. Now you should be able to check that and make sure that you can draw this, given this, and back and forth. This is called a half adder, though, because this carry unit goes nowhere. That is a half adder. So when we're carrying, it's calculated, but it doesn't go anywhere. But to get a full adder, and a full adder allows us to add 3 binary digits. And if they were all were 1, we would have a carry of 1. So this would be 1 and 1 and 1 is what we call in decimal 3. But this is one group of 2 to the first power plus 1. So you see, what happens is we take a half adder, we add these first, and then we add these, the sum of these two, with R in another half adder, and we combine that and we get a table that's like that. So this enables us to add 3 binary digits. Now if we take 2 full adders like we had and 1 half adder up here, we can be used to build a circuit that will add 2 3-digit binary numbers P, Q, R, and STU to obtain a 4-digit sum. And here's the picture of that. Now this is called a parallel adder because you see you're adding R and U, and then you're adding Q and T, and then you're adding P and S. So you have a half adder here, and you have 2 full adders, so we have a parallel adder. Parallel adders like this could be constructed to add binary numbers of any finite length. Now, when we start subtracting, we have to think about this a little bit differently, and we define a concept called the 8-bit 2's complement for any integer a that's between this, and we're talking about a being a number. This is the decimal representation. So, and when we talk about the 8-bit 2's complement for a positive number, we just get the number itself. But it's really quite complicated, or much more complicated anyway, when we talk about the whenever a is negative. And this is again called the 8-bit 2's complement. Now, to find the 8-bit 2's complement for a negative number, what you do is, this is a shortcut, and this is actually how the calculation is done. You take the 8-bit binary representation for a, the absolute value. Again, this is going to be a negative number, but this is the absolute value of a. You switch all the 1's to 0's and all the 0's to 1. This is called flipping or complementing the bits, but then you have to add 1 in binary notation. Now, if you do that, what will happen is that you will end up with, this is the representation that you will get for all of these integers in decimal form. and you see that this is exactly the binary representation. But for the negatives, you get a 1 in the first place. Now, this allows us to represent the 256 integers from minus 128 through 127. When we talk about a more realistic 32-bit, and we'll talk about even 64-bit a little bit, 2's complement need is used. You can get more than 4 billion integers, but this is talking about the concept of how it works. We already talked about this being how we would do the calculation for the 8-bit 2's complement for a negative number. To find the decimal representation, then, what you do is, of the negative integer with a given 8-bit 2's complement, you apply the 2's complement procedure to the given 2's complement. You're basically reversing yourself, and that ends up being the decimal equivalent of the result. So, to test your understanding, let's give you this a try. What is the decimal representation for the integer whose 2's complement is this? Let's see how you do. Let's see how you did. Okay, so since the leftmost digit is 1, you know that it is negative. So if you apply the procedure, what you do is you flip the bits. So the 1s become 0s and the 0s become 1s. And then you add 1 to the result. So you're adding 1 to this number, getting this. And that ends up being 87. And that's the absolute value of minus 87. And we knew it was negative because we had a 1 in there in the first part. So the answer is minus 87. You can check directly from the definition and you'll get the same answer. So at least in this instance, the shortcut. Now, the nice thing about this, the main advantage, is that when you add and subtract integers in their 2's complement form, what you really do is you can use the same circuitry that we've already described, because a minus b is the same thing as a plus the additive inverse of b. Let's talk about an example. So here what we're going to do is we're going to do 78 minus 46. And in fact, this is the representation of 78, and if you check, this is what you get for minus 46 in its 2's complement format. So now we add them. What happened is you do get a 1 out here, but we just discard that because that is outside of the range. But if you discard it, what's left is this, which is, let's see, 1, 2, 3, 4, 5, 6. That is 2 to the 5th power, which is 32, which is the correct answer. So the general procedure for using 8-bit 2's complement to add two numbers is two integers between that range. Convert both to their 8-bit 2's representation. Add them using ordinary binary addition, discarding any carry bit that occurs in the to the 8th position, and convert the result back to decimal. Two things here. One thing is that if you're talking about 64 bits, you can go from the integers range from 10 to the minus 10 to the 19th to more than 10 to the 19th. So there are many integers you get without producing overflow, and we talked about a 32-bit system. You can represent 4 billion integers this way. You can detect overflow pretty easily because here, as an example, if you're adding two negative numbers, you would get minus 133, which falls outside of the range that we have. But when we discard this, we say, oh, we took two negative numbers, add them together, and you get a positive. The computer recognizes that as an overflow. I'll see you in part 2, where we're going to explore briefly a different topic, solving recursion formulas, which frequently arise in the study of